Here's more about trapezoid rule. First, I'm going to do a real quick example. Now that we've got the formula, just a real quick example to cement the process. If you have tabular data, for example, which is the most common case we're going to use the trapezoid rule for. And then I'm going to talk about why it's called the trapezoid rule. It won't be hard. So here's another example. I want the total increase in money in my bank account if the daily net rate of income is given by this table. So I sample every 30 days and I see how much money it's coming in each day. I'm hoping that those are fairly representative. It's not wildly different on different days. And I'd like to get the total amount in my bank account. Well, that's the net change theorem. The total change is the integral of the rate of change. And so I'm really just going to be doing an integral again. And I want to get an accurate thing from tabular data, and the trapezoid rule is the best way to do that, usually. The best simple way to do it, at least. And here's the formula. Okay. So I'm just going to copy that formula down here. And I'm going to put in what all the appropriate quantities are. It's still equal spacing. All the subintervals are equal. Those are 30 days. Okay. And then I'm just going to plug in all of the internal points. So I got $75 on the 30th day. And so I'm basically assuming that for about 30 days around the 30th day, I'm going to get about $75. That's the best estimate. Similarly for 90. Similarly for 100. And similarly for 105. Okay, and if I had more data points, I would have a bigger sum in here. So that's all of the interior data points counted full strength. And then I look at the rate I was getting it at the start and the rate I was getting it at the end. Because those are hanging off the ends, they don't have as much weight, and they get weighted by a half. I make sure 1, 2, 3, 4, 5 summands times 30. That makes sense because there's 1, 2, 3, 4, 5 month-long intervals. It wouldn't be right if I had more than 5 things here. Okay, and then I just let the computer do that. And I get 13,275. What are the units? Well, it was days, 30 days, times dollars per day, so it ends up being dollars. So that's how much money total has been coming in. Okay, so it's really pretty straightforward, tabular to trapezoid, especially if you have this equal interval thing. Okay, so let me talk about why it's called the trapezoid rule, and then that'll help us figure out what happens with unequal intervals. So let's go to the picture here. Suppose I have a really simple case. I've just got like 2 intervals, and I've got A and B. That's my whole interval, and I've segmented it up into just 2. It's pretty minimal, pretty lazy to just do that many, but it gets the idea across. And in fact, the main thing is going to happen in just the first subinterval. The contribution to the left endpoint method would be this rectangle on this subinterval. And the contribution to the right endpoint method would be the whole of the big rectangle. And the question is there a way to think of the trapezoid rule as just some other shape, some other simple shape here that's between the left and right endpoint? Well, definitely. Here's a way to create a shape that automatically has something that's the average of the area contributed by the small rectangle and the big rectangle. Just add half the difference, or in other words, make a trapezoid by making this straight line between the 2 points. Notice it's a trapezoid on its side. We usually think of trapezoids, like in geometry class, looking like this, with the parallel bases being horizontal. This is just something where the parallel ones happen to be vertical. You can still call them bases, but it's a little bit weird because they're vertical. Okay, so this is a trapezoid on its side. And the idea is simply that we're just drawing a straight line between these 2 points. Another good way to think about it is I'm taking this curve and I'm saying, what's a good approximating curve to this? Well, the left endpoint method, let's actually continue this over here. The left endpoint method would be like this, and the right endpoint method would be like here, these rectangles with this height or this height. Basically, the left endpoint method says, I'm going to take the real thing, the orange curve, and I'm going to approximate it by a function that's piecewise constant. That's constant, then a jump, constant, then a jump. That's a pretty terrible way to approximate a function. The right endpoint method also does that. I'm going to approximate it by this function that's like this, then like this. That's a pretty terrible way as well. A better way to approximate the function would be draw straight lines. Hey, that gets much closer already. Okay. And then I'm just going to say, I'm going to take the area under that straight line, piecewise linear, but not piecewise constant approximation of the function. That's definitely a better idea. The only downside might be if it's super hard to calculate the area of a trapezoid. But it's not. That's something we do in geometry class. Okay? And in fact, guess what? in this particular case, the area of the trapezoid is just halfway between the area of this rectangle and the area of this rectangle. Okay, so that's why it's called the trapezoid rule. Let me actually just draw real quick one with more subintervals. So if we had A here and B here, and here's our function like this, and we have more subintervals like this, then all we do is what we're really doing, and one good way to think about it is we're just connecting the dots. We're just going connecting those dots, produce a straight line function, and we're just getting the area of that trapezoid, and the area of that trapezoid, and the area of that trapezoid, etc. Okay? So that's the basic idea of why it's called the trapezoid rule. So now, let's see, actually I think I want to go back to the one subinterval, or the maybe two subinterval case. Okay? So let me redraw that picture real quick. Okay? So maybe just like I had before. Okay. So I want to figure out another way to think about where the formula comes from, how this trapezoid idea connects to the algebra, because it's going to let us do the unequal case. So let's just look at the area of this trapezoid. Okay, so this length is delta x, and then this height here is f of a, and then this height here is f of x1. Okay, just because I picked the leftmost subinterval, so it's from a to x1. Okay, that's not terribly important. Okay, so the area of this trapezoid is just a rectangle and then a triangle on top. Okay, so the area, let's see if I can fit it over here. Actually, let me put it over here since I've got the room. Okay, the area of that single trapezoid is just going to be the area of the rectangle. That's what I'm getting from that, maybe that left endpoint method there. That's wrong D, delta x times f of a plus, and then I'm adding in half of a delta x times, what is this? What's the height of this guy? It's the difference in those two heights. x1 minus f of a. Okay, so the delta x comes out as a common factor, as it always does. Ooh, that's cool. I didn't expect that symbol. Okay, and so what am I getting? I'm getting the f of x, getting f of x1 with a half, and f of a with a half. So it's just delta x over 2 times f of a plus f of x1. Hopefully this is not too shocking. It's delta x, it's the width times the average height. Oh, let me put that in math mode. It looks better. Okay. When you've got a trapezoid like this with parallel vertical sides, here's a nice way to think about the area of that trapezoid. It's just the width of it times the average height. It's got a low point here, it's got a high point here. On average, it's right in the middle. And so it's just width times average height. One way to think about that is I'm taking this sloping roof and I'm pivoting it right in the middle. I'm going to lose this area, but I'm going to gain this equal area. And so it's as if it's a trapezoid or a rectangle with a height that's on the average between the high height and the low height. Okay, so this is how I like to express it. This derivation just kind of happens once, and I like to express it this way. Each trapezoid is just width times average height. So the total, if I have a bunch of these guys, so I have over here, I have another trapezoid that I want to find out. There, I just use the same thing, width times average height. Okay, and then I just sum it up. So in general, so this works for unequal spacing. This is the key thing. I take the t sub n is the sum, let me write it not in math mode, it would be better, sum of width times average height. And let me do an example about how that'll work, and then that'll finish up this video. So here's an example. Let's go back to this bank account example and we'll modify it. Suppose I wasn't particularly careful about sampling these guys at equal intervals. I did day 0 of the year, day 10, day 40, let's leave it at 90, day 120, and then day 200. Okay, and I suppose I have the same amounts coming in on those different days. Okay, so I still want to get total net income. It's still an integral. The income should still be the integral of the rate of from dt, now from 0 to 200. Okay, and that's going to be approximately equal to t sub, there's still 1, 2, 3, 4, 5 intervals. Oops, lost it. T5. Okay. But what's that going to be equal to? Let's see. So, because these intervals are equal or unequal, I'm not going to be able to factor out the delta x as a common factor. I cannot use these kinds of formulas with like the 1, 2, 2, 1 or the treat all the equal interior points equally and then average of the first and last. Those are great when you have equal intervals. Here you have to do it more by hand. We have to just consider this first interval. We take 10. That was 10 days, and my estimate for how much money I'm getting coming in over those 10 days is not 50, which would be the left endpoint method, and it's not 75, which would be the right endpoint method. It's just the average of the two. It's really very reasonable. If somebody had to guess, in these first 10 days, what's a good guess for on average how fast was the money coming in? Well, average of 50 and 75 is really a very reasonable answer. Again, it's something that students often come up with on their own. Next time interval, 30-day interval, and I want to figure out what's my best guess for between t equals 10 and 40 on average, how much was coming in. Well, I have no idea if this is really correct. I could have had a windfall at day 20, but this is my best guess given the data. Okay. Plus, next interval is 50. Width of the interval times the average height on the two ends, 90 plus 100 over 2. Plus, and I'm losing it. Let's see. Next interval is 30, and it's 100, 105. Plus 30 times average 100, 105 over 2. Plus, and then the last one, it's an 80 interval, and it's 105 and 95. Plus 80 times the average of 105 plus 95. Okay. You'll notice that these numbers, the 75 shows up twice, the 90 shows up twice, the 100 shows up twice. When these were equal intervals, that was the basis of simplifying this calculation to use one number only once, and it was a little more efficient. But because these aren't equal, I really can't do that. Now I'm curious. I don't know if I don't think it'll evaluate this for me. I think it doesn't understand when it's not on one line. Okay, but very easy to calculate to get the total integral. So the main thing you just have to remember is the universal rule that always works for trapezoid is sum of width times average height. And it's very similar to the left or right endpoint. It's just for each interval you don't pick one or the other, you average the two, and then you keep going. And if these widths are different, that's okay. That's not a problem. If the widths are all equal, if the delta x's are equal, then you have a little bit of a shortcut, which is that one delta x is a common factor times the sum of all the interior values plus the average of the first and last. But if you only remember one thing, it would be this, because it works no matter what.